All right. These are multiple choice, but let's see if you can solve them without the multiple choice.
Is that 16?
Uh-huh. Okay.
Is that just
Hold on.
9A?
Hold on.
Oh, my. Okay,
If A is equal to 3, what is this expression equal to?
Does that mean you have to times the 3 times 3 first in the parentheses?
Yeah, in fact, I like the problem a little better when we don't say A is equal to 3. What is this quantity equal to? First of all, let's do this one. What's that equal to?
81.
What's 3A quantity squared? Square both of them. In other words, you square the 3 and you square the A. So now what's 9A squared minus 3A squared equal to?
6.
6A squared.
Okay.
Okay. In other words, as long as you have the same things, you can subtract them or add them. If I had 9A cubed minus 3A squared, I would not be able to do anything with that. Okay? In other words, I cannot subtract or add these two things because this is an apple and this is an orange. Well, up here, they were both apples. In other words, as long as you're dealing with the same thing, you end up, if that's an apple, then I have 9 apples minus 3 apples equals 6 apples. Now, their original question said, what is this? Let's see. So we know that that's equal to 6A squared. Now, when A equals 3, what is that equal to?
18 squared?
Square it first. In other words, the 6, you can't multiply the 6 times the 3 and then square it. Because this 2 is not operating on the 6. In the same way that this 2 didn't operate on this 3. This 2 here did operate on that 3 because that was in parentheses. So the first thing you want to do is substitute 3 for A, square it, then multiply it by 6. Okay, and then multiply it by 6. 54. Remember, anything multiplied by 9, the digits have to add up to 9. 56, they would have added up to 11. Okay. How can we do this problem? And this is a multiple choice. They don't want a number here. They want an expression. In other words, here's a case where we have different bases, right?
Mm-hmm.
So we can't merely add the exponents. We don't have the same base. We also have different exponents. So it's difficult to combine this unless we do this trick. I'm going to write the number 4 as 2 squared. In parentheses, always, because we still have to cube it. Okay? Now, what properties of exponents can we use to simplify that? What is 2 squared cubed equal to? 2 to what power?
5.
No, we're exponentiating. So we're always going to do one level less with the exponents. So here we're going to multiply the exponents.
Okay.
Okay. So now we have 2 to the 4th times, well, I can rewrite this thing as 2 to the 6th. Now we got the same base. So I can operate on this. What's that equal to?
4 tenths to the 10th power.
I'm sorry, I couldn't hear you.
4 to the 10th power.
No, you leave the base the same and then add the exponents. So when we're multiplying or dividing, if you have b to some exponent times b to a different exponent, that's always equal to b. We don't change the b, but we add the exponents. Okay, so that's how we get 2 to the 10th. All right, let's do a little algebra. What's the square root of x equal to?
I don't know.
Well, I got the square root of x by taking the square root of both sides. Okay?
Okay.
So, in other words, is all I have to do to answer this is to take the square root of the right side. In other words, I can do this. Starting from that alone, I can take the square root of both sides. You can always do the same thing to the left as long as you do it to the right. And now what's the square root of x equal to? What's the square root of 9a squared?
3a squared?
3a.
3a.
Notice why. 3a times 3a is equal to 9a squared. In other words, here, when we multiply the same base, a's, and they have an exponent of 1, we're going to add the exponents. So the a becomes a squared.
Okay.
Okay. So if I said this, what's the square root of x?
2a?
Good. Not sure I like this problem, but first of all, can you simplify this at all?
Yes. No.
No, you're right. We cannot. In other words, we can figure out what the numbers are. 4 cubed is 64 and 4 squared is 16. So I could do that. But I can't apply any rules of exponents here. In other words, it's the same base, different exponents, but we're not multiplying or dividing or exponentiating. We're subtracting. In other words, if I had the expression x cubed minus x squared, that's essentially what this is, that's your simplified answer. That does not equal x or anything that you... In other words, again, it's harder to add and subtract than it is to multiply and divide. We are seeing that over and over and over again. So basically, what's important to know about this is you cannot reduce it.
Okay.
All right. Now here, the exponent is in, the variable is in the exponent. Okay? So can you solve this? 3 to what exponent would equal 27?
7. No, 9.
Not 3 times an exponent. Remember, when you have an exponent, it means you're multiplying that number together however many times this exponent says. If I told you that it was a small whole number, what would you answer? It's either 1, 2, or 3.
3.
Right, because 3 cubed is equal to 27. Okay?
Oh, okay.
Okay? Let's review our squares. One of the really important things when we're working with roots and powers is that you know your perfect square numbers up to maybe 6, up to 10, and that you know your perfect cube numbers up to a smaller amount. So, what's 1 squared?
1.
2 squared?
4.
What's the next one?
3. No, 9.
Next one?
16.
Next one?
25.
Next one?
36.
Next one?
Are we at 7?
49. 7 squared. Yes, we're on 7. Okay. And
Yeah,
this, the next
49.
one after 7 squared?
64.
And next one?
81.
Okay, you know your square numbers pretty good. Most people do. It's surprising that even if you're not perfect on your multiplication tables, everybody knows their perfect square numbers. It seems. That's important. Let's go. Let me not get ahead of myself here. If we have square roots of numbers and we are trying to simplify them, like that one. In other words, it's not satisfactory to give an answer like this. Let me back up a step. The square root of a times b is always equal to the square root of a times the square root of b. Okay, that's where we're going to start from. In other words, if I have the square root of 3 times 4, that's equal to the square root of 3 times the square root of 4. And then the square root of 4 is what?
2 square root 2.
Just 2. So this would, in other words, this turns into a 2, which I'm going to put in front, and then the answer is 2 square roots 3. Okay? But this principle that the square root of two things being multiplied together equals the square root of each of them being multiplied together is what we're going to use to solve this problem. The square root of 20 is equal to the square root of what times the square root of what?
4 and 5.
Yeah. And the reason, what we're looking for is for one of these factors to be one of your perfect square numbers. Because now I can write that as 2 root 5. Okay? What if I had the square root of 10?
2 and 5.
Correct. But notice, neither of those numbers is a perfect square number. So I can't pull a whole number out of here. So I can change square root of 10 into square root of 2 times square root of 5, but it's not considered a simplification, as all I now have is 2 square roots instead of a whole number times a square root. So we don't do this one. We never do that. Square root of 10 is considered simplified. Let's do some others here. Let me think for a moment. What would that equal?
20 and 20.
Remember, you're looking for factors of 40, one of which is a perfect square. So I don't want to do 8 and 5, because neither of those are perfect square numbers. can you think of factors of 40 where one of them is a perfect square?
Is 10 a perfect square?
Huh?
Is 10 a perfect square?
No. For it to be a perfect square, it has to reduce to a whole integer, a whole number. In other words, we went through the perfect square numbers, remember? 4, 9, 16, 25. Those are your perfect square numbers. So we're looking for a factor of 40 that might be one of those numbers.
Oh, you can do 10 and 4.
There you go. In other words, that's the square root of 4 times the square root of 10. Well, we already know that's as simplified as we can make it. But what's the square root of 4 again?
2.
So that becomes 2 root 10 is what square root of 40 becomes. I'll do a few more of these just for practice. This turns out to be a huge skill. What's that equal to? I mean, a hugely necessary skill when you get into algebra.
2 and 50.
What is the square root of 100? Is that a perfect 10? That's a perfect square number. So it's just 10. In other words, sometimes you don't want to notice that if we'd have made it 2 and 50, we'd have kind of gone backwards. If I make that square root of 2 times square root of 50, now neither of these is perfect square numbers, and I'm left kind of still looking for the answer. But so you want to know your perfect squares up to 100 at least. So if the square root of 100 is 10, what's the square root of 200 equal to?
20.
No. 20 times 20 is 400. That's what you always have to check, is when you take the square root of a number and you come up with a number, make sure that when you multiply that number together, you get this answer.
102.
There you go. So it's the square root of 100 times the square root of 2. What's that become?
10 square root 2.
Right. 10 square root 2, exactly. All right, let's go on a little bit. What's that equal to?
-1.
Positive 1. In other words, because the negative sign is in the parentheses, what I'm doing here is -1 times -1. Negative times a negative becomes a positive.
Okay.
What's that equal to?
-1.
You got it. What's that equal to?
+1.
Okay. So when we have an even exponent, our answer is 1. When we have an odd number, in other words, if I said 5, goes back to -1. Because I would have 5 negatives times each other. That ends up negative. So, if I tell you that Q is an odd integer greater than 1, odd integer greater than 1, what's this answer?
What?
Q is an odd integer. Give me a list of odd integers greater than 1.
3.
Keep going.
9.
Okay. with all of those odd integers, what does this thing equal right there?
-1.
Okay, and then add +1 to -1, what do you get?
Oh, 0.
Okay, all right. I thought you knew it. You're just making you forgot to add that to it.
Yeah.
All right. Here's another kind of problem that
So is it just 32x?
32, not x, but 32 to the x power.
Oh, okay.
Okay? And because the exponents was the same, it was both x, and the base was different, I could do that. In other words, that's the same thing as 4 times 8 to the x power. There's also another way I could do this problem, and that's by turning each of these numbers into the same common exponential base. What is that? What's the common exponential base between 4 and 8?
4.
Actually, it's 2. In other words, I can't write 8 as one base. I can write it as 4 times 2, but here's what I'm looking to do. I'm looking to write 4 as 2 squared, and I'm looking to write 8 as 2 cubed. That's what I mean by common exponential base. In other words, I can express the number 4 as some power of 2, and I can express the number 8 as some power of 2. Now, let's proceed, and what does that equal to?
The 2x?
2 to the 2x, exactly. In other words, we're going to multiply those two exponents, and then we're going to multiply that by what?
2 to the 3x.
And then we're going to do what?
Aren't you subtracting it?
No, multiplying it.
Oh, okay.
So what do I do with the exponents when I'm multiplying? No, don't multiply the bases. In other words, whenever you have this kind of a problem, the answer is 2 to what exponent?
5x.
Right. Okay, what positive number, when squared, is equal to the cube of the positive square root of 16?
The positive square root of 16?
Yeah, let's work this backwards. The last part of the sentence is equal to the cube of the positive square root of 16. Well, what's the positive square root of 16?
4.
Okay, so they're saying something is equal to the cube of 4. Well, there's the cube of 4. And they're saying what number, x, some number unknown, squared, is equal to the cube of 4? What's the cube of 4?
Is that just 4 times 1 squared?
Yep.
64.
Okay, so now let's solve this equation. If x squared is equal to 64, what's x equal to?
8.
Right. And there's your answer. It's good. All right, let's deal with some of these. Let's talk about negative exponents for a moment.
Okay.
What does 3 to the minus 2 mean?
Negative.
No? Okay, that's the first thing that negative exponents do not mean, is a negative number. And that's the mistake that most every student I have makes. A negative exponent merely means we're going to take that thing to the other side of the fraction line. That's what it means.
Oh, okay.
Okay? If I had 4 to the minus 3, then it would be 1 over 4 to the positive 3. If I have 1 over 2 to the minus 3, notice I'm now in the denominator. Well, all you do is move it to the other side of the fraction line and change the sign. In other words, that's equal to 2 to the positive 3 over 1, but we don't need the 1. Okay? So the secret to negative exponents is you just move them to the other side of the fraction bar and change their sign. In other words, this y to the minus 2 down here, I could put that in the numerator and make it y to the positive 2. When you have a problem like this, just take it one variable at a time. In other words, the first variable we want to simplify is the x. What's x? What's this part equal to?
X squared.
Yep. What's this part equal to? You can do it two ways. You can take the y to the minus 2 and move it to the other side, and then we're multiplying y times y squared. Or we're doing division, is all you have to do is subtract the exponents. What do you get when you subtract 1 minus a minus 2?
Negative 1.
1 minus a minus 2.
3.
That's what our exponent on y is. No, you're right. It's 3. Okay, in other words, the two negative signs become a positive. And finally, the z's. What? Boy, I got a big echo there. So what's the z term?
The 7.
We're dividing. So what are we going to do with the exponents?
Subtract them.
So what do we get?
1.
Z to the 1, or just z.
Yeah.
So that's how you do that problem. That looks like a very hard problem, but it's actually a very easy problem. You know, the whole problem is subtracting numbers that are less than 4. This was 3 minus 1. This was 1 minus a minus 2. And this was 4 minus 3. So these are really the easiest problems that look hard. All right, good place to stop. We're making good progress, I think. I will talk to you on Friday.
Okay, thanks. Bye.
All right, Jenna, bye-bye.